Good morning everyone. Today we are going to see the dynamic related problem, that is Allpairshortestpath. So Allpairshortestpath, it is a graph related problem. Here we have given a graph G is equal to V comma E, be a directed graph with n vertices and E is the set of the edges. So this graph first we represent as a cost adjacency matrix, such that C of I comma I is equal to 0, means all diagonals first we consider as a 0. After that, C of I comma j is the length or cost of the edge I comma j if I comma j belongs to the edges of the graph. Otherwise, C of I comma j is equal to infinity if I is not equal to j and I comma j not belongs to the edges of the graph. Then Allpairshortestpath problem is to determine a matrix A such that A of I comma j is the length of a shortest path from I to j. Means we have to find out a shortest path between every pair of the graph. Here we consider that this shortest path start with one vertex I and go to vertex j may travel through some intermediate vertex. So if k is an intermediate vertex on this shortest path, then the subpath from I to k and k to j must be the shortest path from I to k and k to j respectively. Using this, we generate a raised to k of I comma j represents such that a of I comma j is minimum of either this path goes through the vertex k or it does not goes to vertex k. So clearly initially a of 0 is equal to a raised to 0 is equal to C of I comma j, means cost adjacency matrix as it is we consider as the first matrix a raised to 0. After that we calculate a raised to 1, means this is the path which start from vertex I, goes through vertex 1 and then terminates at vertex j. So in this way we travel from a raised to 0, then a raised to 1, a raised to 3 up to a raised to n. A shortest path from I to j going through no vertex higher than k either goes through vertex k or it does not goes through vertex k. If it goes to vertex k, then a raised to k is equal to a of I comma j is equal to a raised to k minus 1 I comma k plus a raised to k minus 1 k comma j, means it indicates that this path goes through the vertex k, that is from I to j. But if it does not goes to vertex k, then as it is whatever in the previous matrix a raised to k minus 1, we consider a raised to k I comma j. So combining this equation we get a raised to k I comma j is equal to minimum of either the path in the previous matrix as it is or the path goes through vertex k. So among these, which is the minimum, that we consider as a raised to k I comma j, where k is always greater than or equal to 1. Now this is the simple algorithm for Allpairshortestpath. Here first we represent this with three parameters. Cost of the matrix, means cost adjacency matrix. A is the matrix that we are going to generate and n is the number of vertices. Cost 1 to n is the cost adjacency matrix of the graph, as already I have explained in previous slides. So a of I comma j is the cost of the shortest path from vertex I to vertex j. Initially cost I comma I is equal to 0. So for I is equal to 1 to n, for j is equal to 1 to n, a of I comma j is equal to cost of I comma j. So whatever the cost from I to j as it is we copy in the first matrix, means this is the cost adjacency matrix. Now once we get the first cost adjacency matrix, then we move towards the value of k. Either it goes through vertex k or does not goes to vertex k. So again here we use three simple for loops and then we compare minimum of a of I comma j, whatever in the previous matrix as it is, or if it goes to vertex k. Among these, whatever the minimum, that we consider as a of I comma j. Now we'll see how this works with one simple example. Suppose this is the given graph, directed graph with three vertices 1, 2 and 3, and these are the costs which are assigned to these edges. Now according to this cost, first we create a cost adjacency matrix and call it as a raised to 0. So from this we can get this matrix. Initially all diagonals are 0. Now 1 to 2 there is a path with cost 4. So I write here 4. Now 1 to 3 there is a path which cost 11. Now 2 to 1 there is an edge of cost 6. 2 to 3 there is an edge of cost 2, and in this way here you can see 3 to 2 there is no edge. Means that here we assign it as an infinity because the edge is not available in the graph. Now next a raised to 1 we are going to calculate. So this is the result of a raised to 1. So here we are going to see whether it goes through 1, path goes through 1. If it is minimum, then that we are going to consider. The first row as it is comes in the second matrices. Similarly, this first column comes as it is in the second matrices. Now we compare the remaining 4 values. Diagonals are already 0, so we compare this 2 to 1 to 3. So if you see 2 to 1 to 3, it is 6 plus 11, 17, and in the previous it is 2, which is less than 17, and that's why previous matrix value is less than the new value that goes through vertex 1, and that's why we keep it as it is. Now we go for this one, that is 3 to 1 to 2. Now 3, if you can observe this, 3 to 1 it is 3 and 1 to 2 it is 4, means 3 plus 4 it is 7, and in the previous case it is infinity. So among infinity and 7 minimum is 7, and that's why we replace this infinity with this 7, and here we get this a raised to 1, that all path goes through vertex 1. Similarly next we calculate a raised to 2, means the paths which goes through vertex 2. In that case the second row comes as it is and the second columns comes as it is. So diagonals are 0, so this value and this value 0, means we need to compare this value and this value. Now check 1 to 3 that goes to vertex 2. So 1 to 3, if you can observe, 1 to 3 11, and 3 to 1 to 2 is 4, and 2 to 3 it is a 2. So 4 plus 2 it is a 6, and previous matrix if we see it is a 11. So new value 6 is minimum than 11, so we replace the 11 by 6. Now in this case the path from 3 to 2 to 1. So 3 to 2 there is no path, and that's why we not necessary to compare this. We write is as it is. Now we move towards the next, that is a raised to 3. So in a raised to 3, third row comes as it is 370, and third column comes as it is. Now these two diagonal values as it is means we need to calculate or compare only these two values. So first calculate 1 to 3 to 2. So 1 to 3 it is 11, and 3 to 2 there is nothing, and that's why this value as it is in the previous matrix 4 we are going to write it. After that we are going to compare or calculate this value, that is 2 to 3 to 1. So here now we can observe 2 to 3 it is 2, and 3 to 1 it is 3. So 2 plus 3 is 5, and in the previous matrix it is 6. So 5 is less than or minimum than 6, and that's why we replace 6 by 5. And in this way we here get last matrix, that is a raised to 3, which indicate the shortest path between every pair of the graph. If there are 3 vertices, so we calculate it up to a raised to 3. So how many number of vertices in the graph, that number of matrices we need to calculate.